Thank you. So I will tell you a slightly different story perhaps than what we've heard before. No tables, no classifications. We're just going to start with a D-wave altermagnet and more from a spintronics perspective going to try and find phenomena that are unique to D-wave altermagnets. So this is work done with Pointer is very weak. With Hyro, who's here of course, and Alexander Moog, who is not here anymore but was in the beginning of the week. And so that's going to be a story in two parts, and the first part is going to be about spin demons. So this is this work that we recently published. So let me walk you through what we mean with spin demons and why we believe them to exist in D-wave altermagnets. So to understand spin demons, we first need to understand plasmons, so they are very much related. So a plasmon, as you're probably well aware, is a oscillation of the electron density mediated by the Coulomb interaction. You can think of these things also as actual quasi-particles, as shown by Pines and Bohm in 52. And so this is a very intuitive picture of a plasmon as just some oscillation of the electron density. And so in a normal metal, of course, we might have multiple bands, and then the simplest thing you can think of is a plasmon which consists of this in-phase oscillation of these two bands. And and so what Pines then asked the question in 56 is what happens if you have two bands but they're non-degenerate, so they have slightly different properties, like different Fermi velocities. You can also generate these out-of-phase oscillations. So he called these things demons because it's sort of backwards. I think his logic was he wanted to name a particle after Maxwell, who didn't have a particle named after him. So he called it a demon and then made up this backward acronym. Make of that as you will. Some people also call these things acoustic plasmons for reasons that will become clear. And they're just out-of-phase oscillations of electron densities in two bands. And this picture is a little bit simplified because I should stress here that these two bands need to be different. If they're degenerate, if they're the same, you're not going to see these type of demons. So this was all done in so the way Pines envisioned these things is, for example, in heavy and light bands in semiconductors, and then these bands have different Fermi velocities, and we will see these demon. And so they have different properties, of course, these plasmon and the demon. They're both mediated by Coulomb interactions and related to electron density oscillations. But the plasmon disturbs the charge density. This is in-phase oscillation and therefore couples to light. And this makes the plasmon relatively easy to detect optically. It's also the reason why plasmons in 3 dimensions, for example, they're gapped at this frequency, this plasmon frequency. This is, of course, optically very easy to detect. But this demon does not disturb the charge density and therefore does not couple to light, and this makes the demon very hard to observe. So there was an observation in 23, which I don't think everybody agrees with, because you have to do some more complicated measurements and you have to make sure that your material consists of two bands which are sufficiently different. And then the main difference in this demon is that it's has a linear dispersion, and it's gapless. This is why people also refer to these things as acoustic plasmons, right? Because it has this acoustic dispersion. So in 3D, this holds. Of course, in 2D, the plasmon dispersion is different as this square root.
Was that material strontium ruthenate?
Yes.
I said, was that material strontium ruthenate?
Yes, it was strontium ruthenate. Okay.
How was the observation made?
Sorry?
How was the observation made? Eels.
EMEals. Momentum resolved.
Yes,
eels.
momentum resolved eels. Yes, exactly. Yes, okay. So the question we then set out to ask is, what if we change these bands to be spin polarized? What type of plasmons and demons can we then find? So if just very simple intuitive picture, we replace these bands with some spin polarized bands, we again find some plasmon which disturbs the charge density, but because it's always in-phase oscillation of these two spin densities, it does not disturb the spin density. But then the demon, you can clearly see just from this intuitive picture that it will disturb the spin density. So we would expect this demon, if we're looking at spin polarized systems, to have some sort of spin character, and this was indeed shown in 2014 for some two-dimensional electron gas, if you play some tricks with the spin polarization, that this can be the case. And these, again, they still follow the same linear dispersion for this. And this is what we call a spin demon, so a spin version of the demon. And now the question, of course, is can we find these things in D-wave altermagnets? So we're going to replace now our bands with D-wave altermagnetic bands, and then we're just simply going to solve for the plasmons and see if spin demons roll out of this story. So very simply, what do we do? Well, I don't need to introduce D-wave altermagnets to you, I think. So we're just going to take two bands at the Fermi surface as given. They follow this nice quadratic dispersion, and they are spin split. And so we're just going to do random phase approximation on these two bands. And this random phase approximation is going to give you plasmons, and it's going to give you, hopefully, spin demons. Yeah, and then the thing that we are interested in the end is we expect the spin demon, because it's a spin full particle, we're going to expect it to appear in the chi-SZ sector. So we're going to focus on this chi-SZ, which is defined formally in the random phase approximation like this. And then the important thing is this dielectric function down below here. So if this thing has zeros, then we see poles in the chi-SZ, and we're going to associate those poles in chi-SZ with a spin demon. So we're going to first analyze this dielectric function, and this is, of course, we can fully calculate this for a D-wave altermagnet. And so I'm going to show you here, I'm going to walk you a little bit through the dielectric function, because I think it's a very neat thing, and you might even remember this from like your very long ago classes, that in a spin-degenerate three-dimensional electron gas, the dielectric function looks like this. So it's going to start here at the density of states at the Fermi level. It's going to have this sharp drop down. So the real part, the real part's going to have this sharp drop down, and then it's going to reappear again. And then we see, if we look at the zeros of these things, we see two zeros. We see a zero here, and we see a zero here. So the second zero is the plasmon frequency, and it lives, importantly, outside of the imaginary part of the dielectric function. So this is this dashed line here. And so, therefore, in the random phase approximation, a plasmon is completely undamped. And there is also this zero here. Sometimes people also call this an acoustic plasmon. I don't think people, it's a very, well, it is an acoustic plasmon in the sense that if we were to solve for this thing, it would be linear dispersive, but it has a big problem, which is that it lives right here in the part of the electron-hole continuum where its imaginary part is largest, which means that if you were to solve for this thing and calculate its damping, it will be very large, meaning that this acoustic plasmon can never be measured. But now what we do is we now take, we take two of these bands and we look along a direction in the Brienne zone where the spin splitting is maximal, so for example along an x-axis. And we're just going to calculate now this dielectric function, which is what I show you here. And again, you might recognize basically that we've taken two of these pictures and sort of overlapped them on top of each other. And we can now simply count the zeros of this dielectric function. We see 1 0 here. This again is a zero, but it lives at this very large imaginary part of the dielectric function, so we expect this to be overdamped. There is a third zero here. This is also going to be, we expect to be overdamped. There's a zero here at the very end, but that's the ordinary plasmon. And so we hope, because if you look at the second zero here, that it corresponds to a slight dip in the imaginary part of the dielectric function. And we're going to hope that this is going to give you a spin demon. Yes, yeah. Yes. Right, but the problem is, so we need to also, we cannot do just a qualitative assessment, right? We have to also look at what is actually the amount of overlap with this imaginary part of the dielectric function. That's another way of saying what is the overlap with the particle-hole continuum. And so we need to quantitatively calculate these things in order to see what is the damping of this spin demon. So this is actually what I'm going to show you here. So I'm going to show you here a color plot of chi-SZ, the imaginary part of chi-SZ, meaning that if this thing peaks, we have a zero here, and therefore we have a strong response in chi-SZ. And okay, it's hard to see probably on the screen, but you see here this very dark blue peak. and it's rather sharp. And so actually this dashed line here is this same line cut that we take in this dielectric function. It lives right above threshold.
Right above it.
Yes, right above the threshold. So these dashed lines here is the edges of the spin-resolved particle-Hall continuum, and it lives right above the minority particle-Hall continuum. And this, because it lives right above, this enables this spin demon to be damped but not over-damped. Yes, so you might ask, okay, yeah, very well, but what has this to do with an altermagnet? So the first sign I'm going to show you is now, this is a function of momentum. Now we're going to keep the momentum fixed and we're going to rotate in the altermagnetic spin split plane. And then you're going to see this very nice picture where you see this resonance, which is going to follow this fourfold symmetry like this. And this is already an indication, and this is a property of the altermagnetic band structure, but you might also, if you're might wonder, well, okay, it's just a fourfold symmetry, so is it not related somehow to the crystal symmetry, just being fourfold, having this fourfold symmetry? And there is another, so one indication why it's not the case is that if you were to look at these bands, that actually, so they are, if you rotate 90 degrees, they look the same, but actually if you look at them, the minority and the majority have swapped. So one is being composed of mainly plus, mainly up electrons, and the other is composed of mainly down electrons. This is what I indicate with these colors here on the ring. And to make this a little bit stronger case why this should then be an altermagnetic spin demon. Oh yeah, okay, sorry, I should stress. So we can actually, so from these types of plots, we can do numerics and we can do analytical calculations of what the property of this spin demon. So we can derive that it's linear, and most importantly, we can derive the quality factor. So that's the ratio of the line width to the eigenfrequency. And we can see that this quality factor, depending on where you live in this altermagnetic spin plate, can be much larger than 1, and therefore we think these things should be, you can measure these things and they're relatively well defined and long-lived quasi-particles. Of course, all these things here depend on altermagnetic band structure values, so they will change depending on what type of D-wave altermagnet you have. Right, so I promised you that this was an altermagnetic spin demon. And the way we show this is that we ask the question, if we now apply a magnetic field along the Neal vector, what is the change in energy of our spin demon? And that's formally just the same as asking the question, what is the magnetic moment of this spin demon? And there, if we calculate this numerically or analytically, we can very clearly see that depending on where you sit in this altermagnetic spin split plane, that the sign of this magnetic moment switches as you rotate through the plane. And this is why we claim that this is a altermagnetic spin demon, and it carries over all these symmetries. And it even has a rather sizable magnetic moment, but you have to sit in this region where also its quality factor becomes quite poor. So this scale is a bit disingenuous. So here it's will only be like 1% of a Bohr magneton, I think. Right, so how would you now ever go about detecting this? So you can, in principle, use some spin polarized eels. So where you shoot electrons with some known spin polarization and you again split them at the detector. So this is spin polarized electron energy loss spectroscopy, momentum resolved. This is very difficult to do as far as I understand, but it can in principle be done, and this directly probes our chi-SC, SC, the imaginary part of chi-SC, SC. So in principle you could map out these types of plots, and we check that it sits sort of roughly in the right energy range. So you can in principle measure these types of spin demons. Of course, actually doing spills on these types of systems will be more difficult, but can be done. And for the experimenter, so you don't even need chi-SC, SC, I think. So this thing also appears in chi-N, SC. So you don't need either the spin filter here or the spin polarizer here. You can get away with only spills where you only either spin filter or you polarize your spin beam, your electron beam. All right, so to conclude this, this first part, I've shown you that there is a new collective mode in D-wave altermagnets, the spin demon. So it's an acoustic mode, so it's gapless and linear at close to zero momentum. It carries magnetic moment with a D-wave symmetry, so this is why we call this an altermagnetic spin demon. It leaves signatures in chi-SC and chi-NSC, so these can be picked up through spills. And this is not a generic feature of altermagnets, so we do not find this in either G-wave or I-wave or also in alt-wave magnets. These things don't exist because in their end it's both a qualitative argument, which is where the Fermi surfaces, the particle Hawk continua split and we find the spin demon, but it's also a quantitative problem. Is this splitting large enough to actually see, to suppress this damping and to see a high quality factor? And it turns out in G-wave and in I-wave this does not work sufficiently well, so the spin demon remains slightly overdamped. All right, very good. Then I will end this first part and I will go to the second part, which is really a spintronics question. So we were asking, we have all these nice D-wave altermagnets, and how can we?
If instead of a lattice model, as in most of these cases are, you get that in the continuum, as I did long ago with Suchan Zhang, Kai Sun, and Konjong Wu, there you get a complicated, well, not a rich spectrum of Goldstone modes associated with the rotational symmetry also associated with this, which some of those modes will be gapped because of the lattice coupling. So they will no longer be Goldstone since the symmetry is now discrete. But I think this is probably one of the modes that survives.
Yes, yes. So we didn't do lattice models, we just did some long wavelength continuum model, so there's no lattice.
Okay, but then you should have seen all the other modes. There are many more, there are more, because the symmetry that you break in that case is SO3 cross O2, which is the rotation in space. Many more Goldstone modes, which are linearly. Some actually are overdamped.
Yeah, so we see four modes effectively. So 1, 2, 3, and there's another normal plasmon mode.
Right, but they have different characters.
Yes, yeah. Okay. So, but the 1 and the 3, they are overdamped.
Yes.
And they're just associated with the normal acoustic, like this first acoustic plasmon here, but.
Right, but these are, nevertheless, these modes actually, if you actually were to stay in the continuum, will make the state a non-Fermi liquid.
Yes, yeah, because you're doing.
Because essentially it will wipe out the quasi-particles. Okay, and so in that sense it's interesting. Now this in some sense is an academic point because the actual system has the C4 symmetry of the lattice, and so some of these overdamp modes will be gapped.
Yeah, so I think these types of acoustic plasmons, they're also relatively well studied numerically, so people have done like RPA on DFT type bands, and then they do see these type of acoustic plasmons and they live all over the place.
Well, not all over the place.
Well, okay. they're hard to classify.
They are really Goldstone bosons, okay? That's the reality, except that they are overdamped. Okay?
Yes.
The same thing happens with the nematic, actually. Mm-hmm. It's the same issue.
Okay, yes.
Okay, but we studied that in 2007, I think. So we actually described these things, but it was clear that the things were going to be overdamped because they are in, they are in the continuum in that sense, as you say. Okay.
Yeah, one way to get these things to be not overdamped is to look at couplings with the lattice itself, and then you would have some sort of acoustic plasmon consisting of, I think, what people call like ion and electron systems. I think that's also work, but that is it's hard to get these things to be under.
Before they get gapped.
Okay. Yeah. Okay, yes, so now this is really, so I was saying a bit more of a spintronic story. We have these D-wave altermagnets, and now we sort of asked the question, what can we do with these things from a spintronic perspective? And of course, the most interesting thing in the D-wave, or one of the interesting things in D-wave altermagnets, is you can use them to generate spin currents, and we were asking now the question, can we use surface acoustic wave to generate spin currents, and particularly not just in metallic D-wave altermagnets, but also in insulating altermagnets, where the primary response will be the magnons and not, of course, the electrons. So a very brief overview of what a surface acoustic wave is and what this field is. So surface acoustic wave is simply some deformation of the lattice which lives on the surface. And what's well known is that a surface acoustic wave will generate a piezoelectric field because it's typically generated in a piezoelectric. And this is going to drag, and if you put on top of this some metal or semiconductor, it's going to drag an electric current with it. This is the acousto-electric effect. The same mechanism has been proposed a couple of times and maybe even been measured in magnon systems, where it's not just the piezoelectric field, but it's actually the deformation of the lattice, which is going to couple to your magnons, is going to drag them along and generate a magnon current. And so what we're proposing is relatively simple setup. You take some piezoelectric, you would excite the surface acoustic wave in it, and on top of it you put some D-wave altermagnet, and then you ask the question, what type of spin currents can I generate? And for completeness, we're also just including some heavy metal layer on top, where the spin current can enter and be converted into a charge current through the inverse spin Hall effect. So we're just proposing to get some realistic numbers out of it, some closed experimental setup. And I'm going to focus here on the fact that this is also going to work in insulating altermagnets. So we're going to have an electric field from the surface acoustic wave, but there's also going to be a deformation coupling to the lattice and a lattice coupling to the magnons. And through this way I will show you can generate magnon spin currents, a magnon spin splitter effect. And so let's very briefly discuss what are magnons in D-wave altermagnets and what do we expect from them. So I think this picture has even been shown before. So in a ferromagnet you have a quadratic dispersion with only one chirality of the magnon mode. In an antiferromagnet you have a linear dispersion and the two magnon modes are degenerate with opposite chiralities. And then in an altermagnet along specific directions, the magnons with opposite chirality split, and you get, in principle, therefore, if you were to excite these, if you were to look at this altermagnet, you were to excite a magnon current, you would also expect a magnon spin splitter effect. And then microscopically, so this is just related to, I think this was also discussed yesterday, the day before, right? That there is exchange values along the diagonals which have different values, and this directly, if you put this into a Heisenberg exchange Hamiltonian, you directly get out of this magnon dispersion that I show you here. And of course the difficulty is how do we now excite a magnon current and generate this magnon spin splitter effect? And this is where we propose surface acoustic waves to maybe come in handy. So I'm just going to flash, just to explain to you very briefly what we did. So this is the electron case. There it's all very straightforward, old school physics. So we have an piezoelectric, which means we have a piezoelectric field. So we just have an electric field at a certain frequency and and we have a certain wave vector, because this is a traveling surface acoustic wave, of course. So we can do all the standard Boltzmann type of theory with a first order response, which is going to go at this frequency omega of your surface acoustic wave, and then you can, if you want out a DC current, you can just look at this second order response. Of course, this will be second order in electric field, so it might be weaker, but it gives you a so a DC response and a 2 omega response. We can work all this out, obtain closed expressions, and the result is relatively straightforward, and it just shows, it's just as you would expect. So it depends on, it directly reproduces results if you were to apply an electrical current, because in the end this is what you are doing. So this is just the spin splitter effect, but second order in electric field and at a finite frequency. Okay, but now for the magnons it's a little bit less straightforward, because as you might remember here we just simply put in this force of the electric field, but for magnons they don't feel the electric field, they don't feel a force necessarily, and so we have to sort of work our way around this. And the way we did this is we just asked the question, okay, we have this surface acoustic wave that typically excited on resonance, so they are linearly dispersive surface acoustic waves. They're typically slower than magnons, so if we sit, for example, here, we excite the surface acoustic wave at this frequency and momentum, and then we ask the question, okay, so we cannot have direct hybridization with the magnons. This is what people also do in ferromagnets, because there you do allow, because it's a quadratic magnon dispersion, you do allow direct hybridization. But we don't have this here in an antiferromagnet, and of course, so this is what's going to happen. Is not direct hybridization, but from the point of view of these thermal magnons, which live way up in energy at kBt, which is way higher, of course, than this surface acoustic wave, which have gigahertz max, a few gigahertz. So from the perspective of these high frequency, short wavelength magnons, there is going to be a lattice deformation, which is going to be very slowly traveling. And in the Boltzmann equation, this is just going to reproduce to you, this is going to give you a force. This is just a classical wave packet approximation, where you say we have a wave packet, and the wave packet sees slowly moving disturbances, and that's just the force in the Boltzmann equation. And so this way we've sort of gotten around this problem of a force for the magnons. We have, of course, now to work out what is the effect of our lattice deformation induced by the surface acoustic wave on the magnon. So to do this, we're going to take a simple lattice model like this. So this is some rutile compound, and we're going to include modulation of the exchange bonds through the surface acoustic wave, through deformation of the lattice. We can work all this out, so we have some sort of strained Hamiltonian as a function of this Rij, which is in the end related to the surface acoustic wave. We can calculate the force from this just from taking the derivative. And so we now have a formal force, and we can put this back into our Boltzmann formalism, do all the same steps with the electrons. And we end up with, again, a second order current. Exactly the same steps, except now we've replaced the electric field with some effective force here, which we have close expressions for. We can calculate all this. And the other noticeable thing is that because we're now directly coupling first to the lattice and then to the magnons, we're also capturing this 4-fold crystal symmetry. And because we're doing second order response, we're even seeing an 8-fold response. So don't be afraid if I show you now the results and you see some sort of extra modulation. So let me walk you through. So this is the spin current generated through the surface acoustic wave. It neatly, as we rotate the surface acoustic wave. So it neatly follows for the electrons, the blue line, it's going to follow neatly our spin splitter response, so vanishing along nodal lines, etc., and peaking here. We also make some estimates, so I show you on the right hand side what would be the voltage in the platinum. This is, we believe, measurable. Of course, it depends on a lot of other variables, like what you use for your D-wave altermagnet. The interesting thing, I think, is the magnons. So we took some set of parameters, and we're actually taking the same set of parameters for the surface acoustic wave for both the magnons and the electrons, with the difference only that the magnons live in an insulating altermagnet and the electrons live in the metal. And so what we see, first of all, is that the magnitude of the magnon response is comparable to the electrons. This is a good sign, because it indicates that this might be feasible to implement in insulating D-wave altermagnets. And then there is this, again, like we see this D-wave symmetry, so it's vanishing along the same nodal lines as the metallic case, but there's an extra modulation. This extra modulation here, we can calculate what it should be, and it's just this 8-fold response, because your surface acoustic wave is sometimes sitting along bond. It's causing a deformation along bonds, along directions in your lattice where it cannot directly couple to the lattice, and therefore it's going to vanish or it's going to be weaker. This we all understand from calculations. Okay, and then we can vary many things. We can vary the thickness, and we can vary the frequency. And here the takeaway is, because I think we're running a little bit over, the takeaway is mainly that we can calculate these things, and the magnon response in quite a lot of regimes can be comparable to the electron response. Most notably in thicker films where the piezoelectric field is being screened, we see a strong magnon response which doesn't care about the screening of your electric fields, but only cares about the deformation. And again, if you use frequency, you can maybe even tune between magnon and electron responses. With the caveat, of course, being that what we took here is magnons in an insulating altermagnet where we expect them to have long lifetimes and relatively good magnon conductivities. If I were to replace this orange line here with parameters for a metallic altermagnet where you have Stoner excitations and other damping mechanisms, it will probably be weaker, because in the end this is transport, which means that if your magnons are not mobile. If they're overdamped, then we're not going to see much of a transport. So you shouldn't take these two lines as being the same thing in the same device.
And the whole estimate of the magnitudes always depends on the magnetoelastic coupling, yeah? So
yes, but this is
So you just-
seemingly universal. There is this Magnon-Grüneisen parameter, and this is always roughly 3 in a wide range of materials. Of course, we don't know this for...
Oh, okay. So you're saying like from this the response would not vary wildly between systems because you know whether you have a strong spin phonon coupling that is very much materials dependent. Yeah.
Yeah. So the magnetic Grüneisen parameter is related to like the prefactor here, right? Somewhere here.
Yeah. Exactly.
And this is seemingly universal.
Okay.
So it's the same in GUNNIK and in some antiferromagnets and in some other ferromagnets. It doesn't change so much. At least it's 3 to 5, whatever order of magnitude.
Okay.
The same. Okay. You can measure this. This is related in the end. You don't need to do complicated measurements. It's related to change in volume as you cool or something like this. You can relate it to some entropic quantities.
Okay. Thanks.
May I ask a naive question? So, have you tried to look at the same effect in pure antiferromagnets? Because naively, I would say that this, at least the relay surface acoustic wave, is equivalent to the spin pumping into the system. And if you pump spin into the system, it does not matter whether you have altermagnet or antiferromagnet.
We were careful to take a surface acoustic wave which does not carry angular momentum.
Okay.
So these are not
it's
really.
Not relay.
It's not really. It's some other wave which. But you are right. If I'm putting angular momentum into the system, why? Yeah, you should get it out somehow. And also because I have some geometry here, right? So we're also talking about spin currents which are going out of the plane. So there is some conversion going on. So yeah, it's not this mechanism. So like I say, insulating altermagnets might be promising candidates to implement this. Maybe also to observe the spin splitter effect. All right, so to conclude this, I've shown you that surface acoustic waves can be used to probe electron and magnon responses in these altermagnetic thin films, and that you can maybe expect some large responses in the insulators. But of course, all depends on material parameters and on having an insulating D-wave altermagnet. But that's a problem for not me. And then this surface acoustic wave community, they are very well capable of creating all types of surface acoustic waves, and you can play with the different types of symmetries and different types of lattice couplings you would generate with different surface acoustic waves. With that, I will leave my summary slides, and thank you.
So, please, questions? It was not enough coffee, or what?
Yeah, thank you. I just wanted to ask, as someone who's not so familiar with the surface acoustic waves, is there some advantage? So similar to a question before of using surface acoustic waves.
Yes, so they have some advantage. One big advantage is that there is a whole field that is doing this in devices, so it's very mature. Like your phone has a surface acoustic wave in it for some specific purposes. That makes it useful. And so in principle, it also means that even though you're in an insulating system, your surface acoustic wave is being driven electrically. So you in principle have electrical excitation, so you have some electrical generation of spin current. And that's hard to do in an insulating system, of course. Yeah, and then, I think the main benefit of these things is their technological maturity.
More questions?
Thank you. So in your collective mode calculation, you argued that the higher order altermagnets, you won't see these modes because the damping effects are too big. Is there an easy way to, essentially, right, the damping became too large for those. Is there a way to see that as some consequence of more spin crossings? Is this why it's too large? Or
Yeah, I think so, because in the end, the thing you need to have is you have two particle Hall continua, and you need to basically separate from the spin up, spin out. You need to separate them as much as possible as you project along directions in your plane. And the edge of the particle Hall continua is determined by q dot your Fermi velocity. And so the question you're asking is for a specific q, what is the difference in Fermi velocities of my spin up and my spin downs?
I see.
And so I think there is maybe some geometrical argument that you cannot fit, right? You have to fit them, you have to rotate 6 times for a G wave, and that maybe you can never fit a large separation in this.
I see. And then a follow-up question to that. So here you find the modes in the D wave case, but is that very sensitive upon your choice of model? Like, for example, if you had a very different Fermi surface?
Yes. So one problem is that, so we really need this type of Fermi surface, because there's also, for example, Fermi surfaces which would, well, actually, I think this is a nice picture. Like, it doesn't have to be like this along gamma, right? So it can also be, like for example, here, if you look at this D wave, and actually you were to do this thing that I said, right? You project along a certain direction and you look at the Fermi velocities. Well, this Fermi velocity and this Fermi velocity, they're actually equal. So even though you would have energetically a large spin splitting, you're not going to see a large difference in Fermi velocities. Okay. So you have to be you have to find the right material. There is some follow-up work that someone else did some calculations on some leap lattice, and they did I think they do DFT, fit to type binding, do RPA, they see something. They do see a spin demon, but it depends on the parameter.
Because the other question I had is, okay, you can draw an altermagnet with a Fermi surface, but you're not guaranteed that that Fermi surface is in the right place to guarantee the stability of the altermagnet in the first place. And so in DFT, you find some stable altermagnetic state, you get a Fermi surface from that, and then you know it is stable in that case, and you use those parameters. Is that?
Yeah, exactly. Okay. But then, and then if you're not able to do this long wavelength electron, then you have to do the RPA on the full time binding, and then it might, like I say, depend on where are my Fermi velocities.
Okay.
I have a quick question. By symmetry, we would expect that some of these overdamped modes become underdamped along some directions.
You mean these?
Depending which way they propagate.
Yes. So this is what sort of it's hard to see on these types of plots, but so along the nodal line, it does vanish. Yes, it has to vanish by symmetry argument.
Overdamped in general, but they are underdamped in some directions.
Sorry, then are we talking about the spin demon or about this 1 or 3 model?
Well, okay, these are all models. I mean, these are, as I said, pseudo-Goldstone modes of the altermagnet. And the altermagnet, if in the continuum, it has actually exact Goldstone modes, which on generic directions are overdamped, but in some directions are underdamped.
Yes,
okay.
I agree. Yeah, okay, then so along these high splitting directions, these modes are underdamped.
Right.
So that is the perspective you take,
Right.
yes.
And you see that.
Yes, yeah, and we also see, so we took a 3-dimensional altermagnet. If you rotate out of the spin split plane, the spin demon also disappears. Like it should, because you're not.
More questions?
Okay.
Then, yeah.
I have one maybe silly question. In the second part of your talk, you drew your spin current and your electric responses, and they seem to have very different scales, right? So you had microvolts, and then you had, I can't remember, amperes per meter square, or not,
Yes.
yeah, okay, yeah. And then you said that those are the same? Was there an easy...
One thing is, so this one spin current is we're asking per unit area how much spin is going out of the plane here.
Uh-huh.
And the other question is asking if I now take a normal metal here, I look at the inverse spin Hall effect, what is the voltage being built up?
Okay.
So there is a conversion of area there. So somewhere I'm assuming I'm putting in that how large this lead is.
Okay.
This heavy metal area.
Okay. So should I seriously take the fact that they cross each other in your...
So no, they're completely independent units,
okay.
right? So left and right are just different. They just happen to be linearly, they relate linearly to each other, so I can draw them on the left and right axis.
I see. Okay. Yeah. Okay. Okay. So the fact that these scales are similar, that is meaningful?
No, it's just the fact that I rescaled my...
That's what I was checking.
Like
Okay,
I could have chosen in nanovolts and then it doesn't.
Yeah, so I thought maybe you had a reason to say these scales were similar. There was some... Okay.
Okay. More questions? If no, let's thank speaker again.